when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase, just form factor alone.
The interfaces to what we call the structural battery, where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure. I mean, long term, we want to try to replace about at least 1% of the total vehicle fleet on Earth, which is about 2 billion vehicles. So long term, we want to try to make about 20 million vehicles a year.
Tesla Throwback Thursday. Today we continue our journey of Tesla's 2020 Battery Day. That's right, folks. This is part B. If you're looking for part A, right here. Or you might be able to check it out at the end of this video. Or don't. I'm not the boss of you. This will be a hypercut. As always, the full video is linked below. So without further ado, let's get to it.
First, before we get too far into it, let's talk about what is in a battery cell. We've got the cap and the can, negative and positive terminals of the cell. When you open that cell, you've got a tab connected to those terminals, what we call the jelly roll, which is the wound electrodes on the inside. You can actually see what this looks like as you unwind it. This is over 1 meter long in a typical 2170 cell. To explain what's actually going on here, we've identified we've got anode, cathode, separator, positive and negative terminal. Watch what happens as we discharge the cell. Got lithium moving from anode to cathode, and then the reverse. When we charge the cell, anode moving from lithium moving from cathode to anode across the separator. This is the basic of what makes all lithium-ion batteries, no matter what the form factor is. When we look at what's happened to date, at least in our products, we've moved from the 18650 form factor to the 2170 form factor through great collaboration with our partners, Panasonic, new partners like LG and CATL, and probably others in the future.
The first 2 digits refer to the diameter, and the second 2 digits refer to the length. So that helps explain why are these weird. What's up with these weird numbers? But like nobody could explain to me why there was an extra 0. So like, okay, well, we're deleting the 0 that nobody can explain in future form factors. So that's why it's technically it's like the 18650 bizarrely, but going forward it's the 2170 because we just got rid of the extra 0 because it's pointless.
Simplification is the name of the game, and even when it comes to naming these things, if it doesn't make sense, it's got to get the out of here.
But when we look to the ideal cell design, if we were to do it ourselves, we need to go beyond just what we're looking at us in front of us and study the full spectrum of options. We found a sweet spot somewhere around 46 millimeters. But it's not just about a bigger form factor. Like anybody could make a bigger form factor.
Any fool could make a bigger form factor. We're not any fool.
Yeah, exactly. There are problems as you make cells larger. In fact, supercharging and thermals in general become really challenging as you make bigger cells. We came up with this tabless architecture that maybe you've heard about that basically removes the thermal problem from the equation and allows us to go to the absolute lowest cost form factor and the simplest manufacturing process. This is what we mean when we talk about tabless.
You actually have a shorter path length in a large tabless cell than you have in the smaller cell with tabs. This is a big deal. So even though the cell is bigger, it actually has more power. The power to weight ratio is actually better than the smaller cell with tabs. This is quite hard to do. So it's nobody's done it before. There's a whole bunch of things that we're keeping a little secret sauce here that we're not telling everything. People that really know cells, this is a massive breakthrough.
And so when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase, just form factor alone. Yeah, and I want to stress, this is not just a concept or a rendering. We are starting to ramp up manufacturing of these cells at our pilot 10 gigawatt hour production facility just around the corner.
What? Ramping up production. This is back in 2020, and I'd like to say the progress has been a little bit trying. But when you're doing something that no one's ever done before, you gotta cut these guys a little slack. Battery companies are switching to this form factor. Panasonic, LG, thanks to the ingenuity of Tesla's engineers. Anyone making battery electric vehicles will more than likely switch to this form factor, and Tesla could have easily patented this, preventing others from following in their footsteps, but that's not the goal. Transition the world to a sustainable energy economy. Tesla's not going to be able to build every battery electric vehicle.
But let's stack up everything we just saw at the cell level. So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. When thinking about the ideal cell factory, we have inspirations behind us in the paper and bottling industry. Let's talk a little bit about what's in a cell factory. First, there's an electrode process. Then those coated foils are wound in the winding process we just talked about, where if you do have tabs, you have to start and stop a lot. Then the jelly roll is assembled into the can, sealed, filled with electrolyte, and then sent to formation, where the cell is charged for the first time. One of the most important processes is where it all begins, the wet process of the electrode coating. And when you're looking at this, you're like, wow, that's a lot of equipment for one step, especially when you consider that little speck next to the coating oven is a person. Wouldn't it be great if we could skip that solvent step, which is one of those dig a ditch and then fill it kind of things where you put the solvent in and then take it out and recycle it, and just go straight to dry mix to coat? And that's what the dry process really is about. Literally, powder into film. As simple as that.
I mean, it's hard, actually, just to be clear. So, you know, if this was easy, everyone would do it. And you know, as you go from like benchtop to lab to pilot to volume production, there are actually major issues that you encounter at every level. It's not like, you know, you make something work on your bench and bingo, now you can make a bazillion of it.
Absolutely.
It's insanely difficult to scale up.
Yeah,
yeah.
But if you do scale it up,
Yeah.
what you saw before becomes this.
Yeah.
So you can see the motivation. A 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment.
There's a clear path to success, but a ton of work between here and there.
The key to a high-performing assembly line is accomplishing processes while in motion, continuous motion, and thinking of the line as a highway, max velocity down the highway, no start and stop, no city driving.
Exactly.
Together with our internal design team that makes this equipment and designs this equipment, we coupled thinking about how to make the best cell with thinking about how to make the best equipment so that we could accomplish the fastest parts per minute rates on all of these tools.
This right here, this is one of the major reasons why I'm all in on this company. It's the machine that builds the machine. Now, sure, other companies, they've got their manufacturing process and it's been working for damn near a century. I get it. No big deal there. But Tesla is trying to reinvent how to do things. Building battery electric vehicles is totally different than building internal combustion engine vehicles. And this level of thinking in 2020 about how to perfect the battery form factor, and not only perfect the form factor, but thinking about the best way to manufacture said form factor. Oh, I'm blown away. And like Elon said before, it's not all sunshine and lollipops over here. There's a lot of hard work that needs to go into this.
We were able to get to the point where we can implement assembly lines, one line, 20 gigawatt hours, 7 times increase in output per line. And when you're thinking about scalability and pure effort, having one line be 7x the capability is just effort multiplying.
The factory can be 10 times smaller. And then the other thing is how fast are things going through the factory. It's like speed and density. The faster you go, like if a factory that's moving at say twice the speed of another factory is equivalent to two factories basically. And the company that will be successful is the company that with one factory can accomplish what other companies take 2 or 3 or 4 factories to do. So this is what we're trying to do here.
Your mother Right. It's not what they're trying to do, ladies and gentlemen. It's what they are doing. Giga Shanghai, Berlin, Texas. The machine that builds the machine is way more important than the machines that come out of those factories. This is the base of Tesla's disruption of the automotive industry.
We can design the entire machine to be one machine and remove all of these unnecessary steps.
Basically, Tesla is aiming to be the best at manufacturing of any company on Earth. This is the thing that's actually most important in the long run. Eventually, every car company will have long-range electric cars. Eventually, every company will have autonomy, I think, but not every company will be great at manufacturing. Tesla will be absolutely head and shoulders above anyone else in manufacturing. That is our goal.
Manufacturing is hard, and hard problems are fun to solve. In a typical cell factory, formation represents 25% of the investment. And what is formation? It's charging and discharging cells and verifying the quality of the cell. Turns out we've charged and discharged billions and billions of cells in our vehicles, so we know a thing or two about that. 86% reduction in formation investment, 75% reduction in footprint.
If you've been doing it the longest, you probably figured out a trick or two.
Actually, what this translates to, based on what we know today, is about a 75% reduction in the investment per kilowatt hour or gigawatt hour. It's just basically 4 times better than the current state of the art to the best of our knowledge. You can see, like, basically we can get a terawatt hour in less space than it took to make a gigawatt hour, 150 gigawatt hours. So this is pretty profound. It's like, I would actually not have thought this was possible several years ago. We will continue to use our cell suppliers, Panasonic and LG and CATL. So this is 100 gigawatt hours supplemental to what we buy from suppliers.
Not only is all of that manufacturing innovation fantastic for enabling scale, it's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level. What are the active materials we're going to put in that cell design? Let's talk about the anode first. Let's talk about silicon. Why is silicon awesome? It's awesome because it's the most abundant element in the Earth's crust after oxygen. Why isn't everybody using it? The main reason is because the challenge with silicon is that it expands 4x when fully charged with lithium.
With silicon, the cookie crumbles and gets gooey.
What we're proposing is a step change in capability and a step change in cost. And what that really is to just go to the raw metallurgical silicon itself. Don't engineer the base metal. Just start with that and design for it to expand in how you think of the particle in the electrode design and how you code it. In the end, by leveraging this silicon to its potential, we can increase the range of our vehicles by an additional 20%, just this improvement. Yeah, and when we take that anode cost reduction, we're looking at another 5% dollar per kilowatt hour reduction at the battery pack level. What is a battery cathode? Cathodes are like bookshelves where the metal, the nickel, the cobalt, the manganese, or aluminum is like the shelf, and the lithium is the book. And really, what sets apart these different metals is how many books of lithium they can fit on the shelves and how sturdy the shelves are. And you can see nickel is the cheapest and the highest energy density, and that's why increasing nickel is a goal of ours and really everybody's in the energy in the battery industry.
We need to have a kind of a 3-tiered approach to batteries. So starting with iron, that's kind of like a medium range, and then nickel manganese as sort of a medium plus, intermediate, and then high nickel for long range applications like Cybertruck and the semi.
The cathode process itself is a big target. 35% of the cathode dollar per kilowatt hour is just in transferring it into its final form. And so we see that as a big target, and we decided to take that on.
It's crazy. Like, you're going around the world 3 times. There's like the moral equivalent of like digging the ditch, filling the ditch, and digging the ditch again. It's total madness, basically.
This is how we've always done it. The audacity to think that you can change the way we do things. Yeah, that's what we're all about over here at Tesla.
They're just kind of like legacy things that it's like how it was done before, and then they connected the dots, but really didn't think of the whole thing from like a first principle standpoint, saying how do we get from the nickel ore in the ground to the finished nickel product for a battery. And so we've looked at the entire value chain and said, how can we make this as simple as possible?
We get rid of the intermediate, metal, water, final product cathode, recirculate the water, no wastewater at all. And when you summarize all of that, it's a 66% reduction in CapEx investment, a 76% reduction in process cost, and zero wastewater. Much more scalable solution.
Yeah.
We can also use that same process we showed on the previous page to directly consume the metal powder coming out of recycled electric vehicle and grid storage batteries. So this process enables both simpler mining and simpler recycling. And on that note, the way the lithium ends up in the cell is through the cathode, so then we should obviously on-site lithium conversion as well, which is what we will do using a new process that we're going to pioneer. That's a sulfate-free process again, skip the intermediate. 33% reduction in lithium cost, 100% electric facility co-located with the cathode plant.
Shout out to the facility in Corpus Christi.
Lithium is not like oil. There's a massive amount of it pretty much everywhere. In fact, there's enough lithium in the United States to convert the entire United States fleet to electric. So
Simply mix clay with salt, put it in water, salt comes out with the lithium, done. I
yeah,
mean,
it's pretty crazy.
Yeah. When we get to this steady state, 20 terawatt hours per year of production, we will transfer the entire non-renewable fleet of both power plants, home heating and battery and industry heating and vehicles to electric. And at that point, we have an awesome resource in those batteries to recycle to make new batteries. So we don't need to do any more mining at that point. And you can see why.
Yeah.
The difference in the value of the material coming back from the vehicle versus the ground, you'd always go to the vehicle. And we recycle 100% of our vehicle batteries today. And actually, we are starting our pilot full-scale recycling production at Gigafactory Reno next quarter to continue to develop this process as our recycling returns grow.
Yeah, I mean, to date it's been done by third parties, but we think we can recycle the batteries more effectively, especially since we know our batteries, we're making the same battery as the thing we're recycling. So whereas like third-party recyclers have to consider batteries of all kinds.
All of the benefits that you just saw are added to this benefit of a 12% reduction in dollars per kilowatt hour at the battery pack level. Almost at our halve the cost goal, but there's one more section.
Finally figured it out. So it starts with having a single piece casting, or a single piece casting for the front body and the rear body, making the entire rear section of the car as a single piece, high pressure die cast aluminum. And in order to do this, we actually had to develop our own alloy because we wanted a high strength casting alloy that did not require coatings or heat treatment. This is a big deal for castings, especially with a large casting. If you heat treat it afterwards, it tends to deform. It kind of like does this like potato chip thing. So it's very hard to keep a large casting to have its shape. So in order to achieve this, there was no alloy that existed that could do this. So we developed our own alloy, a special alloy of aluminum that has high strength without heat treat and is very castable. It's a great achievement of our materials team.
It just never ceases to amaze me how cavalier the Tesla team can be. Is there anything preventing us from creating it? I don't know. We could do it. Let's do it then. There is no quit when it comes to achieving the mission.
The interfaces to what we call the structural battery, where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure. It says this, so 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts.
This is the massive difference between an internal combustion engine vehicle and a battery electric vehicle. There are plenty of ways to innovate, reduce cost when you're talking about a battery electric vehicle, if you're constructing it from the ground up. If you're just trying to do what you've been doing for the past 100 years, Legacy Auto, not naming any names, your costs are probably going to be through the roof. Internal combustion engines have been at the end of the line when it comes to innovation and reducing costs. Their eyes, they're just not adjusted to seeing what's necessary like an EV startup might. Honestly, it's not even a fair fight.
That long term, any cars that do not take this architecture will not be competitive.
And it's not just at the product level a better product, but in the factory, it's a massive simplification. You saw the part removal, it's casting machines, it's the structural battery pack. So we're looking at over 50% reduction in investment per gigawatt hour, 35% reduction in floor space, and we'll continue to improve that as we make the vehicle factory of the future. In addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah.
Range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery pack level, and a 69% reduction in investment per gigawatt hour, which is the true enabler when we talk back about how do we achieve this scale problem here.
What this enables us to do is achieve a new trajectory in the reduction of cell cost. I mean, long term, we want to try to replace about at least 1% of the total vehicle fleet on Earth, which is about 2 billion vehicles. So long term, we want to try to make about 20 million vehicles a year.
That's the goal, folks. 20 million vehicles per year. By the time we see these next generation vehicles roll out of factories, don't be surprised when you see a drastic reduction of COGS and a dramatic increase in production for not only batteries, but vehicles as well.
What does it mean for what does this mean for our future products? We're confident that long term we can design and manufacture a compelling $25,000 electric vehicle. Like I said, about 3 years from now, we're confident we can make a very compelling $25,000 electric vehicle that's also fully autonomous. We have and extreme performance and range, and we should probably talk about the Model S Plaid. What about that? We took the latest Plaid out to Laguna Seca on Sunday. It got a minute 30, and we think probably there's another 3 seconds or more to take off that time.
Looks like we'll be saving the Q&A portion, which is always fun to hear, for next week on Tesla Throwback Thursday. Professor Hustle's office hours are in the comments below. Be easy. Peace.